Hello student, I am Dr. Namika Goyal from ABES Engineering College Ghaziabad. Today I am going to discuss about the last topic of Unit 5, that is fast Fourier transform of the subject design and analysis of algorithm. In my previous lecture, we'll discuss about the key areas of algebraic computation. There are key areas of algebraic computation. The first one is the matrix operations. With the help of algebraic computation and the initial time complexity of matrix multiplication is order of n-cube. With the help of algebraic computation, that is a Stratian matrix multiplication, the time complexity of Stratian matrix multiplication is order of n raised to the power 2.81. Our next key areas of algebraic computation is polynomial expression. If we if we evaluate the polynomial expression using Naïve approach, so the total time complexity is order of n raised to the power 2. With the help of fast Fourier transform, the time complexity of polynomial expression evaluation is order of n log n. So let's start our topic. In today's lecture, first we'll discuss about the introduction to fast Fourier transform. After that, then we'll discuss the divide and conquer strategies of fast Fourier transform. And last, we'll discuss the optimized polynomial operation, that is fast Fourier transform. So let's start our topic. First of all, what is fast Fourier transform? Fast Fourier transform, it is a divide and conquer algorithm that efficiently compute the discrete Fourier transform of a polynomial, reducing the time complexity from order of n square to order of n log n. Now, what is discrete Fourier transform? So discrete Fourier transform, it is nothing but it is a mathematical approach, or we can say the mathematical technique that convert a sequence of number into another sequence of number to transform a signal from time domain to frequency domain. So fast Fourier transform basically optimize the computations of DFT, discrete Fourier transform, using a divide and conquer strategies. So first we'll discuss the divide and conquer strategies of fast Fourier transform. The fast Fourier transform basically divide the n size of a DFT problem into a size of n by 2. And here for dividing the n size problem into n by 2, here we use two factors, one for even index terms and one for odd index term. This process can be recursively applied until the size of problem is 1, right? So if I want to discuss about the fast Fourier transform steps, so basically divide and conquer strategies can be categorized into three steps. First step is the divide, second one is the conquer, and third one is the combine. In case of FFT, the step number 1, separate the input into two parts. First one is all the polynomial index, even index terms, and second part will contain all the odd index element. Then after that, the step number 2 is concur. Concur step basically recursively compute the discrete Fourier transform of all even index and odd index elements. And after that, finally, the step number 3, that is combine, which use the symmetry and periodicity of the roots of unity to combine the result efficiently. So, let us take an example to understand first the polynomial operations Naïve approach, and after that we'll discuss the polynomial operations with the help of divide and conquer approach, right? So, if I want to evaluate the polynomial expressions P of x, if I want to evaluate the polynomial expressions P of x, here P of x is equals to A naught plus a naught plus a1x plus a2x square plus an minus an x raised to power n, where a0, a1, an are the coefficients of polynomial. If I want to multiply these two polynomial p of x into q of x, a Naïve approach would compute the product rx is equals to px into qx. And the time complexity of polynomial operation using Naïve approach is order of n square. If I want to reduce this time complexity, here we apply the concept of algebraic computation to convert this time complexity or reduce this time complexity order of n square to order of n log n using fast Fourier transform. So now fast Fourier transform is frequently used to multiply polynomial efficiently. Here first we'll discuss the algorithm of recursive fast Fourier transform. Well, the fast Fourier transform step. Here you can see the step number one, n is equals to a dot length. Total length n is power of 2. When we apply the divide and conquer approach, so it is the mandatory condition that the size of n is power of 2. So if I want to divide our polynomial into n size problem into n by 2, so it is mandatory that our n is power of 2. Then if the value of n is equals to 1, then return a. It will return index value a. Otherwise, if the n is power of 2, then first we'll compute the value of omega n e raised to the power 2 pi I by n. Then we'll initialize omega is equals to 1. Now we'll divide. Step number 1 of divide and conquer approach. We'll divide our problem A will even index terms, and second set is odd index terms. So basically divide our problem into two part, even index term part and odd index term part. So first we'll divide our problem into two different set of problem, and the size of each subset is n by 2, right? And then the step number 2, that is concur approach. What we have to do in concur approach? In concur approach, we have to solve these two n by 2 size problem recursively. Y naught is equals to recursive fast Fourier transform A naught, that is recursive approach. Then again y of 1 is equals to odd index term, recursive FFT A of 1. After computations recursively solve these two set of problem, will step number 3 perform will step number 3, that will be combine these all solution, that is for k is equals to 0 to n by 2 minus 1. Here y of k is equals to y of k 0 plus w y of k 1, y of k plus n by 2 is equals to y of k 0 minus w y of k 1. So here omega is equals to omega into omega of n, and last will return y as a solution. So if you want to compute and analyze this fast Fourier approach for algebraic polynomial operation, so it will divide our problem into n by 2 size, and then will recursively compute the solution and then combine this approach. So the time complexity in that case is, first we'll write the recursive equations of this algorithm, that is 2t n by 2 for the recursively solve the polynomial operations. And after that, what we have to do, we just combine the recursive solution to a single solution. So the combining cost is order of n. So the total time complexity, if I want to solve this equation using master method, so the time complexity in that case is t of n is equals to order of n log n. So this is the basic applications of algebraic computation, that we can evaluate our polynomial operations using fast Fourier transform, order of n square, time complexity to order of n log n. I hope you understand the concept of fast Fourier transform in the case of algebraic computations. These are the references used in our presentation. Thank you.